this is Jaswinder Kaur and welcome to my channel. So today we are going to discuss the assignment that is based on the Rouche's theorem. So let's go for it. The first example is, show that all 5 roots of the polynomial pz is equal to z the power 5 plus 6z square plus 2z plus 10 lie in the annulus 1 less than mod z less than 3. So we have given a polynomial pz and we have to show that all the 5 roots of this polynomial lie in the given annulus. So just see this diagram. The inner circle is of radius 1, the outer circle is of radius 3. I consider 2 circles because the annulus is given to be 1 less than mod z less than 3. So the annulus is this green colored portion, right? So in this diagram I'm having 2 circles. So let's consider these circles. So circle 1 is mod z equal to 1 and circle C2 is mod z equal to 3. These be the 2 circles. Let's consider the first one, C1, that is mod z equal to 1. Now because we have to apply the Rouche's theorem here, which states that if we are having the 2 functions fz and gz that are analytic inside and on the circle, provided with the given condition that mod of gz should be less than mod of fz, then the number of zeros of fz and fz plus gz are same, right? So to prove the number of zeros of fz is equal to the number of zeros of fz plus gz, we need to show the condition that mod of gz should be less than mod of fz. Now here, what should I consider fz to be? Because I want the roots to be in the annulus green colored portion. I want the zeros to be in the green colored portion. I do not want any zero inside the circle C1. So we have to consider the polynomial such that it has no root, right? Because we are considering the circle C1. We are talking about the circle C1 and we do not need any root in C1. That means I have to choose my polynomial fz which has no root. So from the given polynomial pz, we have to choose our fz and gz, right? So what can I choose fz from pz? Yes, pz is z the power 5 plus 6z square plus 2z plus 10. So let me take fz to be equal to 10, which means it is having no root, right? And the rest remaining is gz, z the power 5 plus 6z square plus 2z. Now I am having the 2 functions and both are analytic, right? Now on C1 I have to check whether mod of gz is less than mod of fz or not. If mod of gz is less than mod fz, then I can say that the number of zeros of fz is equal to the number of zeros of fz plus gz. And because fz is having no zero, that means fz plus gz. What is actually fz plus gz? This is fz, this is gz. So it is actually our polynomial pz. So finally, polynomial pz is having no zeros inside the circle C1. This we need to show first, right? So let's check mod of gz. This is mod of z the power 5 plus 6z square plus 2z. This is further less than equal to, yes, mod of z the power 5 plus 6 mod of z square plus 2 mod of z, right? This is equal to, now because we are considering the circle C1 and it is given that mod z is equal to 1, put mod z equal to 1 over here. You get 1 plus 6 plus 2. So this is equal to 7 plus 2, that is 9. And this 9 is less than 10, the function fz. And what is 10? Actually, you can take this as mod of fz. You can also write it as mod of fz. This is fz, which can also be written as equal to mod of fz. So finally we got that mod of gz is less than, strictly less than mod of fz, right? So mod of gz is strictly less than mod of fz on C1. Since fz and gz are analytic inside and on C1, with mod of gz strictly less than mod of fz on C1, now we say that by Rouche's theorem, fz plus gz has the same number of zeros as fz inside C1. But fz is equal to 10. Do this have any zero? No. So this has no zeros inside C1. It is a constant polynomial having no zero, no roots, right? So therefore Pz is equal to Fz plus Gz, right? Which is z the power 5, which is the given polynomial, plus 6z square plus 2z plus 10. So fz is having no zero, so this is also having, fz plus gz is also having no zero inside C1 according to the Rouche's theorem, right? So this also has no zeros. This is a great benefit inside C1, that is mod z is equal to 1. So one thing is clear, right? We are not having any zeros in C1. Now what about this thing is about inside C1. What about on C1? Let's also check this, right? So to check the value of mod of Pz on C1, we have mod of Pz is equal to mod of z the power 5 plus 6z square plus 2z plus 10, which can be, you can write greater than equal to, because mod of a plus b is always greater than equal to mod a minus mod b, right? So this is greater than equal to, I take this first 10, mod 10 minus mod z the power 5 minus 6 mod z square minus 2 mod z. So this mod of Pz, this is greater than equal to this thing. In bracket I am mentioning that mod of a plus b is greater than equal to mod a minus mod b. So you can start from 10 also. Mod 10 minus mod z the power 5 minus 6 mod z square minus 2 mod z, which is equal to, this is 10, this is 1 on C1, mod z is equal to 1, this is minus 6, this is minus 2, which is equal to 1 on C1. So this mod of Pz, therefore, that is mod of Pz is greater than equal to 1 on C1. So whatever the value of z, for any value of z, we got this mod of Pz, this value is greater than equal to 1, right? That is, Pz has no zero on C1 also. So Pz has no zero inside C1 and also it has no zero on C1, because on C1 we get mod of Pz, this value is greater than equal to 1 outside the circle, right? Now consider the second circle. We have checked for the first circle. Now we are going to check the Rouche's theorem for the second circle. What is our second circle? C2 mod z equal to 3. Right? Now I have to prove that all the roots fall inside C2, right? And how many roots should fall inside C2? 5 roots should be there in C2. So I have to consider my fz now to be equal to z the power 5, because z the power 5 is the polynomial having the degree 5. So I can have 5 roots from this polynomial. So we write we take our fz to be equal to z the power 5 and remaining terms for the gz. 6z square plus 2z plus 10. So I have to choose this fz and gz from this given polynomial, which is z the power 5 plus 6z square plus 2z plus 10. Because I need my all 5 roots now inside C2, that's why I consider fz to be z the power 5 now, right? If you consider 6z square, that means you are having 2 roots. If 2z you consider fz, then that means you are having 1 root. How many roots we need? 5. That's why I have to consider fz to be equal to z the power 5, because power is 5. So I can get 5 roots, right? So now we have to check whether mod of gz is less than mod of fz or not. If this thing happens, that means the number of roots having fz is equal to the number of roots or zeros of this pz, and our result is done. So on C2 mod z equal to 3, we have mod of gz is equal to 6z square mod of 6z square plus 2z plus 10. This is less than equal to, I can write 6 mod z square plus 2 mod z plus 10. Put the value of mod z equal to 3 over here. You will get, after putting, this is 6, this is 9, plus 2, this is 3, plus 10, which comes out to be equal to 70, right? And this 70 is less than 3 the power 5. What is your fz? Z the power 5. You have taken z to be equal to 3. So this 70 is strictly less than, you can guess like this, 3 the power 5, right? So which is nothing but your mod of fz. So from here we can say this, mod of gz is strictly less than mod of fz on C2. Now since fz and gz are analytic inside and on C2 with the given condition mod of gz strictly less than mod of fz on C2, by having these two things, now we apply the Rouche's theorem. So by Rouche's theorem, fz plus gz has the same number of zeros as fz inside C2. Now fz is equal to z the power 5 has all 5 zeros inside C2. So therefore, fz plus gz, which is your pz also, which is equal to z the power 5 plus 6z square plus 2z plus 10. This pz is also having all the 5 zeros inside the circle C2. Since we have also proved before that this pz has no zero inside and on C1, but it has all the zeros inside the circle C2. So therefore, all the 5 zeros of the polynomial pz lie in the annulus. Now the roots are lying in the annulus. See the diagram again. What we are saying, we have proved that for the circle C1, pz has no zeros inside this circle C1. But this is your circle C1, this is your circle C2. But for the circle C2, we have proved that pz has all the roots, 5 roots inside the circle C2. Inside circle C2 means all this region, green colored region, right? But in this inside the circle C1, we are not having any zeros. That means all the zeros lies in this annulus mod z greater than 1 less than 3, the green colored portion. So the proof is done, right? So like this way you have to do the examples. We will be doing some more examples in the next video. Just go through this example, right? Alright, take care. Goodbye.